So how I like to think of invader problems are you're being invaded with something, with an acid or a base, a strong acid or base, and it's just like the space invaders come and invade the Earth or whatever, something's going to be left over after the war. Somebody's going to run out, somebody's going to kill off first or whatever. Well, you're going to be left with destruction afterwards. And so what we want to know is after the destruction, everything's done and everything, what's left over. So there are 4 different types of situations. The very first thing to do is when you add that acid or base to the solution, deal with it first, and then see what's left over. And we're going to use stoichiometry to deal with what's left over, which means we're kind of looking at limiting reactants. All right. Our 4 situations are the following. If you are left over with a hydroxide ion or an H plus ion, then the strong wins. That strong won the war, and that's going to determine the pH of the system. If we're left over, if what's left standing is a weak acid or a weak base, then we always have to add those to a Rice table to be able to find out our H3O plus or OH minus concentration. If what is left standing after the war is a salt, which is our conjugate acid or base ion, then we go into hydrolysis. Again, go straight into a Rice table, add it to water, go into a Rice table, and then use your Kw over your Ka or your Kb. And lastly, like we learned yesterday, if what's left standing after the war is a weak acid and its conjugate base, then we're going to use the Henderson-Hasselbalch equation. So we're going to jump into it. This situation that we're looking at here is the following. Let me get there. 125 milliliters of 0.525 molar HCl is mixed with 125 mils of a buffer system. And it tells me what that buffer system is composed of. And it says find out the pH of the final solution, and it's given us a Ka. So very first thing is let's deal with the acid. Okay? So our acid ion, our H plus, is added to a buffer system. Our buffer system is acetic acid and we have acetic acid and the acetate ion. So when I add my H in there, in that buffer, who's going to attack the H? Who wants to be with the H? AC. So we're going to do AC minus. And what we're going to make is HAC. We want to know who is going to be left standing after this invasion. After H plus invaded, who's going to be left standing? So we need a mole table, or if you want to talk, called limiting reactant, but we need to be in moles to figure this out. So we need moles of H plus. So how many moles of H plus do we come in with? We have 0.525 molar HCl, and we have 0.125 milliliters. So we multiply it. Wait. You have this. 0.0656. 0.0656 moles of H plus invades our system. How many moles of acetic acid or acetate ion is in our system? Well, we have 125 milliliters, and it's 1 molar. So that means we have a 0.125 moles of acetate. Acetic acid is the same thing, so there's 1.125 moles of acetic acid. There's 125 milliliters, and it's a 1 molar solution. It's a 0.525 molar hydrochloric acid solution, and there is 0.125 liters. So I multiplied them.
If we're adding hydrogen into the acetate and we're getting acetic acid, what if our moles we want because we already have acetic acid?
What we started out with, what originally is in there. Huh? We're not in a rice table, right? Right now we're doing a limiting reactant. Who's going to run out first? So we're in, what did we start out with? Molarity. And we need to get those into moles. So what molarity we started out with, we need to get that to moles of how much is in there, in the system originally. Remember we're kind of doing like a rice table, but it's a mole table. So.
That, but my thing was just like, I figured like.
No, we're fixing to take care of that. Okay. Who runs out first? Who's going to lose this war? H plus. So that means we need to subtract H plus from the reactant side, that amount of moles. But we're making some on the other side, so that needs to be added onto the other side. That many moles need to be added on that other side. Does that kind of answer that question right there? Okay. So this is what we're left with. After the war, this is what's left standing. What's left standing is a weak acid and a conjugate base. So where do we need to go to figure out the pH? What do we use? Rice table? Is there something easier than a rice table? Henderson-Hasselbalch. So we need pH is equal to the negative log of our Ka, which, let me go back to is 1.8 times 10 to the minus fifth. 1.8 times 10 to the minus fifth plus the log of our ion, which is 0.0594, over our acid, which is 0.1906. If you will see, Henderson-Hasselbalch uses molarity, right? But I used moles. Why is it okay in this situation, just in this situation, to use moles rather than molarity? They're both in how much? They're both going to be in 250 or 0.25. So even if I divided them and put them into moles, my ratio or molarity, my ratio is still going to be the same.
So you would have to convert it back to molarity
if they were both in different volumes. Yeah. But usually this is fine. Yep. All right, so what's our pH? 4.238. So if you're keeping track, this is a Henderson-Hasselbalch situation, or situation number 4 back on our tips. Everybody good? Okay. Next, 125 mils of 0.5 molar NaOH is added to 125 mils of 5 molar acetic acid. What's the pH of the final solution? And it's giving us a Ka there. All right, so deal with the hydroxide. The hydroxide invades, and it is invading acetic acid. When it invades acetic acid, what do we end up with? Water and the acetate ion. Now we need to know who is going to be left standing in this invasion. So we need to get to moles. So we need moles of OH. So everybody should find your calculator, take 0.5 molar and multiply it by the amount, 0.125. 0.0625 moles of OH. Acetic acid is the same thing. And we have waters out of there and acetate ion. There's nothing originally in there. So who's going to run out first? They both are, right? Because they're the same. So we subtract 0.0625, and we're going to add that to the other side. So who is left standing after the invasion? Acetate. So if we're left with an acetate ion, so we are left in a hydrolysis situation. So that means when it's a hydrolysis situation, let's turn this to molarity. So we're going to multiply it by, or divide it by how many liters total. Yes?
So in our first column, let's subtracted the concentration of hydrogen. So we subtracted the concentration of water. And we then also subtracted, did we also subtract the concentration of the acetic acid? And then if so, why didn't we add them both together from the other side? Does that make sense?
Because if OH runs out first, then because OH and HAC are the same, they both run out at the same time.
But because they're used together to make the other one, I thought that makes sense.
Okay,
And you got 0.25 liters because you added milliliters?
the total, yes. So we are left with 0.25 molar acetate ion. So when you're in a hydrolysis situation, what's the first thing you do with your ion? Add it to water. And when we add it to water, we make acetic acid and hydroxide. Our acetic acid, what we come in with is 0.25 molar. No water, no acetic acid, no hydroxide. Our change is going to be minus X plus X plus X.
Why did you flip the equation?
Why did I what?
Why did you flip that equation? Because it was like the opposite.
So what I did is I took this, what was left over, and I have to add it to water.
It just
Oh,
happened.
okay.
So 0.25 minus X, so X is negligible here. And we have an OH, but we have a Ka value. So what do we need to do? So 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5. Because it's a hydrolysis situation, we have the hydroxide ion, but we have a Ka rather than a Kb.
It's the KW.
That's a Kw. It's just a constant. And we're going to set this equal to X squared over 0.25. So solve for X for me, which is our OH concentration.
KW equals KA times KB.
Yes. 1.18 times 10 to the negative fifth molarity. So now we need, using our OH concentration, we need to find our pH. So plug that in to find pOH, which I get is 4.92. And I get my pH, or 3, sorry. And I get my pH as 9.07.
Wait, I have a separate question.
Mm-hmm.
So for molarity, they go to 3 decimal places.
Mhm.
So should we have like technically gone to 3? Or where'd you get the 2 from? Because I always get messed up with this.
I haven't even been paying attention to sig figs, honestly, on this. But it should be 1 sig fig because
Okay.
0.5.
Oh, because the zeros are too long.
So 1 decimal place.
No, those 0.5, that 0.5, you need the least amount of least amount of sig figs. So the least amount of sig figs is 0.5, the first 0.5. So it should be 1 decimal place for our answer. So 9.1. Any other questions before we go on to the next problem? Yes.
Can you explain to me what X is supposed to mean and how we got there?
X? It's a rice table. So it's the stoic, the change. Any other questions? Okay, let's go on. So that was a hydrolysis situation. Now we are going to number 7. So this time we have 200 mils of 0.5 molar sodium hydroxide added to 0.5 molar acetic acid. So we take our strong, we add it to our weak, and we end up getting water and the acetate ion. So OH has invaded HAC, and we need to know who's going to be left standing. So we need to, or who's going to run out first. So we need to get to moles. So if I have 2.2 liters of a 0.5 molar solution, then that means I have 0.1 moles of hydroxide. I do the same thing for acetic acid, and I end up with 0.0625 moles of acetic acid. Have no acetate, and water goes away. So who runs out first? Acetic acid. So we subtract and add 0.0625. All right. So what is left standing after the war? OH and acetate ion, right? So if OH is present at the end, then OH wins the war. So OH wins the war, which means that is what we need to find our concentration on. So we take our moles of hydroxide that's left over. We're going to divide it by our total amount of solution, which is 0.325 liters.
Wait, no.
200 plus the 125. And that leaves me with a concentration of 0.1153. And then we have to get POH. .94. And finally, pH. 13.06.
This situation is strong.
This is a strong situation, yes.
Strong.
Strong acid or the strong base situation. So this would be situation number 1. These are so tedious, but I really like them. All right, next. What is the pH of a 2 molar solution of acetic acid? So these are 3-parter. There's going to be 3 and 4 parts on these. This is like something that you would see from an AP exam. What is the pH of a 2 molar acetic acid? So straight away we know we are working with a weak acid. So how do we find the pH of a weak acid? Add water. So our acetic acid plus water is going to give me my acetate ion and hydroxide ion. So A, we can go straight into a mole table or a rice table. No water. Our change is minus X plus X plus X. X is negligible. And we're ready to solve for X, which is our H3O plus concentration. So we go into our equilibrium expression. So our Ka, which they've given us, is 1.8 times 10 to the minus 5th, is equal to our products, X squared, over our reactants, 2. X is 0.006 molar, and that equals our H3O concentration. And we use that to find pH, and pH is 2.22. All right, let's look at B. A buffer solution. So now we are in a buffer. 0.1 liters of 2 molar acetic acid and 0.1 liter of sodium hydroxide. Compute the hydrogen ion concentration of the buffer solution. So this time we're invading our acetic acid with a hydroxide so that we can make a buffer. So we have been invaded, so that means we need to start out with a mole table, figure out who's going to run out first. So we have 2 molar acetic acid and 0.1 liters, so that's going to be 0.2 moles of acetic acid. We have 0.1 liters of 1 molar sodium hydroxide, so that's 0.1 moles. So who's going to run out first? OH. So we subtract 0.1 and add 0.1. So who's left standing? So acetate ion and acetic acid. So we are in what type of situation? Conjugate acid and conjugate base and weak acid. So we are in a Henderson-Hasselbalch situation. Which means we need to use pH is equal to pKa plus the log of our ion, which is AC, over HAC. Again, I haven't converted these over to molarity. They're still in moles. But I went ahead and crossed out the second part of my equation. And why did I do that? Because they're the same. So it's equal to 1. So in this situation, pH is equal to my pKa. All right. So what is my H plus concentration? So let me show you this. pH is equal to pKa, and our pKa, our Ka, so that's the negative log of 1.8 times 10 to the negative fifth. Right? Cross out the p and the negative log. So our H concentration is what? 1.8 times 10 to the negative fifth. Everybody okay with that? Because we're fixing to throw another situation in here. All right, now let's go to C. Suppose that 1 liter of molar hydrochloric acid, so now we're taking hydrochloric acid and we are going to invade our buffer that we made in part B. So if we add acid in here, a strong acid, it's going to interact with our ion to give us HAC. Before I go any further, I'm going to go back up here and I'm going to get the molarity of our HAC and AC. So I'm going to divide the 0.1s by a total of 0.2 to give me 0.5 molar. Because we're about to use them in the rice table.
Where you did it 0.2.
0.2, because I had 0.1 liters and I added another 0.1 liter to it. All right. Okay, so how many, especially, let's go to the mole table real quick. So the moles, how many moles of H plus did we add? We have 0.5 molar and there's 1 liter, 0.1 liter. So we added 0.05 moles. How many moles of acetic acid and the acetate ion were in that buffer that we added that to. We know we have 0.5 molar, but how many liters did we use of that buffer? Go to the part C, 0.04. So we have to take our 0.5 molar and multiply it by 0.04 liters to determine how many moles of acetic acid and acetate ion. I got 0.02. So who's going to run out first? We're going to subtract 0.02 and add it. And we're left in a situation where we have a strong acid and a weak acid left over. So, who won the war? The strong acid. So we're going to use these moles, that 0.03 moles. So we have H plus is equal to 0.03 moles. And how many liters did we have total in that situation? In situation C, how many liters do we have total? 0.14. So my concentration of my hydrogen ion is going to be 0.214 molar. I like these. They kind of build on each other. And once you do them several times, it starts to just totally make sense. Yes? Uh-huh.
So when we were coming up with the equation, we used part C. We used the ion.
Uh-huh.
Why did we pick the ion just because we're adding nitrogen to it? So
I have a buffer system. So I have AC negatives available and I have HACs available. So when I add my H in there, who's my H going to interact? Yes. Okay, we have time for one more. You guys are going to be sick of these. Plus you have them on your homework. Next, a 4-gram sample of sodium hydroxide is dissolved in enough water to make 0.5 liter solution. Calculate the pH. How do we calculate a pH of a sodium hydroxide solution? We need to first find moles. So we're in a strong base situation. So we have 4 grams. Molar mass of sodium hydroxide is 40 grams in 1 mole. I am in moles right now. I need to get to molarity. So I'm just going to, and I know moles, or molarity is moles per liter, and I know I have 0.5 liters, and that's just a 1 on top. And now you're ready to solve. And I get 0.2 moles per liter. And that is also my hydroxide ion concentration.
It's 0.1.
What?
0.1.
Why is it 0.1?
Well, 4 divided by 40 is 0.1.
Yeah, then divided by 0.5.
No, that's right. Never mind.
Did you get 0.2 as the answer?
Yeah, I did.
Okay. So now we get POH. POH is 0.699. My overall answer, it says it wants the pH, so we subtract that from 14, and pH is 13.301. Everybody okay with that one? Okay, so the next one is suppose 4 grams is dissolved in 1 liter, but it's in a 0.5 molar ammonia and 0.5 molar ammonium buffer. It wants to know the concentration of the hydroxide ion at the end. So now we're going to take our hydroxide ion, so our base, and it is going to invade a buffer. And when it invades the buffer, our buffer is acetic acid and the acetate ion. Who's it going to interact with?
But I thought it was.
Oh, sorry, you're right. Thank you. NH3 and NH4 plus. So it's going to interact with NH4 plus to give me NH3 and water. I need to know how many moles of sodium hydroxide we have. So we have 4 grams divided by 40, 0.1, and it's in 1 liter. So we have 0.1 moles of hydroxide. We have 0.5 molar ammonium, and it's in 1 liter, so it's 0.5 moles of that, and 0.5 moles of NH3. Who runs out first? Hydroxide. So we subtract and add 0.1 to both the sides. And we're left with what kind of situation here? The HH, last year they called it the Henderson-Hasselhoff. So now we are ready to say that POH is equal to our PKB, so that's the negative log of 1.8 times 10 to the negative 5th, plus our ion, 0.4 over, plus the log of our ion over our base.
How do because they just say K, do we just assume that they gave us K?
Yeah, because we're dealing with a base. So POH I get is 4.56.
Wait, why is this POH? The base is on this.
Because of the NH3. And our OH concentration is 2.72 times 10 to the negative 5th molarity.
Wait, how did you do that? Raise 10 to the negative?
Yes, 10 to the negative 4.56. Yes.
I'm still confused on how doing the HH thing gives us the thing of OH, the concentration of OH. Or it doesn't. It's the POH.
It gives us POH, and then we use POH to find OH concentration. Okay, so there's the last one there, and I am going to do that one tomorrow.